Hello everybody, my name is Nitin. I'm going to talk a little bit about iOS Keychain, some improvements on the Keychain itself and how, as a pen tester or a security researcher, it would be useful for you to know some internals of the Keychain. I'm a senior security consultant with NCC Group, just got promoted, so yay. I work a lot on mobile security stuff. I specialize in iOS. I think I specialize in iOS, but there's a lot of work to do. I love to understand all the operating system internals. My current research includes like working around OS X, iOS a lot, but I do work on Windows and Linux as well when time comes in. I'm author of Keychain editor tool that I will be showcasing you in a little bit. As well as Keychain editor UI, which is a GUI app. And this is my first time speaking at a conference, so thanks. Thank you. So the basic outline is very simple, so a little bit introduction about iOS Keychain, why am I doing this talk, evolution of iOS Keychain since its inception up to iOS 9, and then something interesting has changed from iOS 8, and that is the access control object. We'll be looking at it, and then finally showcasing both the tools. So, a system keychain is basically a secure storage within the iOS operating system. You can think of it as a password management tool where you could store all your secrets, certificates, and anything on iDevice. I think it has a cap of 4 MB, but having said that, a lot of secrets will be stored in the iOS keychain, and it should be stored in there. It's a single keychain for all the apps. However, we'll talk a bit about access groups, and that is how the isolation happens. And each app is only able to access its own item, or if it's like a development access group, then you'll have a set of applications from the same developer team, same house, able to access that item. It's maintained as a SQLite database, and that's basically the path keychain to database that's over there. And the general classes for a keychain item is a generic password, internet passwords for Safari and stuff, and then certs and keys, which includes anything like including the digital identities. So those are all the attributes for them. Moving along to the important stuff, that is the data protection. And if you have been earlier to David Schutz's talk, it's pretty similar on how all the cryptographic routines work underneath, and all the key bags that allow an item to get encrypted or available when at any point of time. So I'm not going too deep into the keychain, the cryptographic routines, since that has already been taken care of. So what I'm going to focus is just the user layer, or just the surface of the keychain. And it's very analogous to file system protection, where you have like when unlocked, after first unlock, accessible always, which means when unlocked is only that this item is available when the device is unlocked, and after first unlock is when the item is not available. The item is available after first unlock after reboot. So always is the least protection, and it's never encrypted. So when you think about some considerations, the highest data protection now is available, and this is according to the latest WWDC conference, Security and Your Apps. So when unlocked is the default right now, which is like a little bit contrary to the NS file protection, where in NS file protection it's after first unlock, but for keychain it's when unlocked. But that means that if your app is doing some backgrounding work, you wouldn't be able to use it. So you want after first unlock for backgrounding apps. And the most important thing is that accessible always will be deprecated in iOS 9. But if you still see the iOS 9 API diffs, you see that it changed from a var to a let, a constant. So that means accessible always is still available in iOS 9. So this is just to give some perspective on how an item gets stored inside the secure enclave using the keychain. So the application and security framework are at user space, and your application would use one of the security frameworks APIs like SecItem add to add an item inside the keychain. The security framework runs a daemon as well. That daemon takes care about talking with the kernel on adding the item. However, if you see that key store prior to iPhone 5 or previous devices, they did not have secure enclave. Secure enclave was introduced in iPhone 5s, and the key store was still in the kernel. So that means that all the cryptographic keys that are useful for the keychain items are at the kernel level and very much accessible. It's only from 5s you see that the key store is saved in the secure enclave. And if you have been to David's talk, he basically talks a little bit about secure enclave and how secure it is at present. So you could use either your Touch ID or device passcode to further access one of those items, and we'll talk a little bit more about how that goes about. So, like I said, using the keychain, the available APIs are, it's very small set of APIs when compared to BSides, and there are only like 4. Add, update, copy matching is basically like extracting the keys out of the keychain, and then there is a degree. However, in order to get some more useful features, there are undocumented C functions like get protection and get constraints. So as a security researcher or a pen tester, you would want to know like what kind of protection this item is having and if you want to flag it or not. So these are the functions that will let you know. So these are some important attributes as far as the keychain is concerned. Account name is anything that your app tries to store. So you can think of it as like a component inside your application or just username, stuff like that. So account names can be many for a single application. Service name is basically like an analogous to an app itself. You can have more service names as well, but the account name is like within the service name. And then access group, that is what I was talking about earlier. Access group defines the boundary for each keychain item. So if you do not want to share an item with any other apps, then the access group will be only for your particular option for your application. But but if you have more than one application, you could use this access group to give that item to more number of apps, but it still needs to come from the same development team. It needs to be signed from the same developer. And protections, that is what we are interested. So the accessibility, which I talked earlier, those are always worth looking at. So, research goals, and that is why I'm here today. One of the main motivations behind this is that we all recommend as a security consultants that Keychain is the recommended storage area and stuff. But it needs to be noted that not all developers use the Keychain securely. So most of the times you see that all these items are like use the least amount of protection, like accessible always. And this happens because, and when we talk to developers, we understand that as the app grows big, they do not understand which application needs to be used with the full protection, like when unlocked, or which application needs, which item needs to be used while backgrounding. So if the app does not work for some reason, they just switch to accessible always for all the items, so that the application just works for them. And it's still to this day that we see more and more applications use accessible always. So it is a good area for a security pen tester to look at it and confirm that, like, if an application is using an item in the keychain, it should be secured properly. However, there was previous work, but since iOS 8, a lot of tools have been started to break. And this is because a lot of restructuring was done within the file system, within the operating system as itself from iOS 8. And iOS 8 brought a lot of changes. iOS 9 even brought more changes. So all those previous tools are no longer supported right now. And Keychain is sensitive, so we would want to hack it in case. So the previous work, you guys have already heard about like Keychain dumper or Keychain viewer, which was fairly working well till iOS 6 and iOS 7-ish, but after that it wouldn't work. And the way for a Keychain, where these tools would work, or my tool would work, is only on a jailbroken device, because a jailbroken device would disable all the integrity checks, so like code signing or entitlements check. So I can now have an application with an entitlement as star. So this is what I mean. So like I said earlier, Keychain access group would define like what applications would an item have access to. But if you just give a wildcard entry, that means your application will have access to all the items inside the keychain. Now this works because there is a daemon called amphd which runs, and most of the jailbreakers, in order for them to run their untrusted code, they disable amphd. That's the first thing that they do when they jailbreak. So amphi is the Apple mobile file integrity daemon, and that daemon is responsible to validate this entitlement flag with that of the Apple key. And since that amphd no longer works properly, now we could have an entitlement flag with anything, and we would like to have a star, which means that we can have access to all the items and we could dump it. So the main motivation behind doing research on Keychain and then writing tools is that, like I said, existing tools do not work on your iOS versions. I'm pretty sure iOS 8 and iOS 9, those tools would not work. And we'll talk a bit about the evolution of the Keychain itself, and we'll see that iOS 8 has a lot of changes, and there is no support, absolutely no support. And one of the things that if you manage to run the previous tools, you will see that instead of these long actor accessible unlock, you'll see those short forms AK, CK, DK, which are basically the same thing as these, but those are the internal representations of that. And those tools would just display AK, CK, DK, which gives a lot of problem when we want to look at it. And the dump would be really huge if you are dealing with a lot of applications. The dump would be really big, because Apple itself stores a lot of items in its keychain, and on top of that, there are many applications on the phone. So there is no way to search through all that list. Sure, you could do grep, but it would be nice to have something inbuilt inside the tool itself. And then editing and deleting the keychain on the fly as well. Most of the times what happens is that you test a particular application, but then you want to edit or delete it. Sure, you could delete the application, but deleting the application does not ensure that the item is deleted. So you'll have all the settings in the keychain as is. But you want to delete those items, so now we could use the keychain editor tool to either delete the item, or if you want to edit it on the fly and see if the application behaves differently, you could just edit it. So let's talk about evolution of iOS keychain. So one of the important things that was introduced in iOS 8 is the multi-factor authentication. So up until now, we know that all the items, so when you use like one unlock, the item is only accessible when the device is unlocked. That means that you enter your passcode, your device is unlocked now. All the keys related to those particular items are available right now. So that's why you get those items decrypted. However, So they introduced multi-factor authentication. That means that you need to have another layer of guarantee that you need to tell the system that, hey, this item can be decrypted, and that is by either giving a device passcode or a touch ID. So if you see that now, if you open your banking applications and everything, it asks for another authentication to either give your touch ID. If that fails, you fall back to device passcode. So that is basically a multi-factor authentication. And it's used by both the Keychain APIs and the local authentication API. And I'm not going to talk about local authentication API in this talk because it is only lightly related, but it's still a good topic to explore, but that is not what I'm doing today. So in iOS 8, apart from those accessibility constants, a very welcome change is the addition of when passcode set. And what this basically means is that an item can only be stored in the keychain if a user has set a passcode on the device. So we have still users who do not use device passcode. They do not set device passcode. So if you have like super sensitive application like a banking application, and if the bank really wants to make sure that their application or their customer's data is secure, they could use like one passcode set. That means that it forces the end user to actually use a device passcode. If the application, if the device passcode is removed after the application is installed and it's in the keychain, then that item gets invalidated by default. So that's the new accessibility constant. And then there is this new attribute called access control. And access control is basically what the multi-factor authentication is. So it gives more fine-grained control over each item, like when an item can be decrypted. So the item is no longer decrypted as soon as a device is unlocked. You need to give secondary authentication to it. And for iOS, there was only one policy that was available at that time. That's the user presence. So user presence is basically, that means that either device passcode or touch ID is needed to further decrypt that keychain item. However, in iOS 9, more policies were added. So in addition to user presence, you now have touch ID any or touch ID current set. What touch ID any or current set mean is that, so on an iOS device currently, you can have more than one set of fingerprints enrolled. So I think the max limit is 5 right now. So if you have touch ID any, that means that you could enroll or de-enroll the fingerprints, and it's still a valid set. But if you use touch ID current set, so let's say you have 3 fingerprints enrolled at the time of the application installation, and if there is a 4th fingerprint enrolled after the application is installed, then that item gets invalidated because the current set is not matching with the previous set. So the way it does is that it takes a hash of all the fingerprints, all the 3 fingerprints, and it checks for each time whenever that item is being accessed, and if that hash does not match, like if a finger is de-enrolled or enrolled, then that item gets invalidated. So that is useful. And lastly, the device passcode. So that means that if the device is not supporting Touch ID, then you could just default it to device passcode. Or and are just the logical operators. And then 2 important additions are also the private key usage and application password. Now, private key usage means that a particular item that is being stored inside the keychain will be used to basically sign any data. So you want to have some signed data between the device and the server, between the application and the server. You could specify that an item, that data, can be used as a sign-in key, and you specify that by saying that private key usage. Application password means that in order for that item to be decrypted, it's not just your device passcode or Touch ID. It also requires another password that comes from your application. So that means that in order for an item to decrypt, you need to have 2 passwords. One comes from the application. That could be like hardcoded within the application, or like it could fetch from the server on the fly. and then your device passcode or touch ID. So yeah, so that's basically all the changes that we have, so let's see what basically all those access controls is and why is it useful. So as a pen tester, you know that there is an item over there, and if you figure out that it's being used as an application password, then you want to go further investigate how that secondary password is coming. If it comes from, if it's hard-coded into the application binary itself, so that's bad, that's a finding for us. A good way to do is to fetch it on the fly from the server, keep it in memory, and then discard it as soon as it's used. So for things like that, you really want to know like how the developer actually set the permissions to that particular item. And in order to able to do that, we need to understand what is an access control object. Currently there is no API to see like what. So there is an API to get the protections out, like if what kind of protection it's being used, but there is no API to know what kind of access control that item has over it. So for that we have to do a little bit of reversing, and then understand like how this this access control object is being built. So if you see over here, this is a simple query to add an item. So SecItem add takes in a query. The query is a dictionary with class set to generic password, account name, service name. And if you see over there, that's the access control with ACL. ACL is a constant on the top, which is a written value of SecAccessControl create with flags. So create with flags takes two operations. One is the protection, the accessibility constant. It is set to when unlocked, and the next is actually the constraint or the policies that we seen earlier. That's the user presence over here. So when all these gets into it gets baked into the query, and then it's being added into the keychain. So let's see what steps are being taken when this dictionary is being built. So the first thing we need to know is what actually that constant ACL is. So the written value of this create with flags API call is an optional SecAccessControl. So it's something new in Swift, the optionals. And I really like Swift for this only reason that it gives you optional, where it means that a variable can have a value, or if for some reason that value fails, then the variable is by default set to nil. And if you see that if-let is like a unwrapping of that optional. So the code path is only followed if there is a value in the ACL. If there is not a value, then you could just go into that block and then print out the error. But anyway, so the SecAccessControl is an optional value, and what basically SecAccessControl is internally, it's a structure. It's a C structure with two values. One is the runtime base, and the other one is the dictionary. So runtime base is something that we really do not care about, but the thing that we really care about is the dictionary, because that is where all the constraints are being set. So the first call, when that API is called at the user level, internally the first call is being made to the SecAccessControl create, where it creates that dictionary, it creates memory for the dictionary. And the second call is immediately made to the set protection. The set protection is just at the one, is the accessible when unlocked. So now when you access the structure, the dictionary inside it, you'll see that the protection over here is set to AK, which is when unlocked. And then the next step is that to create a sub-dictionary within that the bigger dictionary. And this sub-dictionary is actually the ACL value. You can see over here from the LLDB, if you dump that particular memory address for that dictionary, you see that ACL is a secondary dictionary inside the main dictionary. And for that ACL, a call is made again to mutable constraints, get mutable constraints. So these constraints are whatever the flags that we given at the user level, whether it's a user presence or not. So now we have a dictionary inside a dictionary that is ACL, and we'll see how that ACL gets filled up. So, like I said, flags determine the overall structure of that ACL dictionary. And if no policy is specified, that is like if you just pass a nil instead of the user presence at the top, then the default ACL is set. So the default ACL means that there is no access control on that particular item. So you'll see when you access the dictionary, you'll see that the ACL dictionary will have a DACL, which is the default access control list set to Boolean value true 1. That means that no access control policies are set on it. However, if a user presence policy is specified, then we get 3 built-in operations set for this item. And the new items are the OD, ODEL, and OE. What OD is, so we'll take a step back and actually understand what these operations are basically. An operation is basically like what kind of an action can be performed on that particular item. So that means that you see OD is op decrypt, so that means that an item can be decrypted. ODEL means an item can be deleted, so that is the operation that can be performed on that item. And OE means that an item can be encrypted as well. And then for private key usage, you'll see opsign. And opsync is for opsync is used for iCloud sharing, iCloud Keychain, which is not used at present yet. So now if you see over here in the dictionary, we'll see that there is OD, ODEL, OE. ODEL and OE are by default set to true because like every item is encrypted by default, right? So whenever the device gets unlocked, by default it just encrypts it. So that is set to true, and any item should be able to be deleted. So again, the operation on that item is like ODEL is set to true. But the important thing over here is that when an item gets decrypted, so it needs to be only decrypted based on a set of constraints that were specified. And the constraint over here is that the CPU is basically the user presence constraint, which is set to device owner authentication. So that means that you can either specify a device passcode, or you could specify a touch ID. You'll be prompted with any of one of those. Instead of user presence, if you have like touch ID current or touch ID any, you'll have a different set of constraint mentioned over here in order to decrypt that item. And similarly, you will see for private key usage as well. So that means that there is a mapping between these operations and the constraints that are being set. And that mapping is basically like when you mention like an item, when you give an access ACL to an item as like a user presence, device passcode, touch ID, and your touch ID current set, by default you'll have these 3 operations on a particular item. These 3 operations are set on that item. So that means that as a security researcher, if you see these 3 items, you would be sure that this item is not being used for a private key usage, but it is being used for one of those 4 above mentioned things. And going further, if we go further, the dictionary will know for sure that which of the constraint that is being set on that device. So if it's a CPU, then you know that it's a user presence. So as a pen tester, you will know that yes, we have user presence set as an ACL for this one. Luckily for me, I was going through some documentations, and luckily there were some undocumented APIs for me, so which from Swift you could just call them, but you need to do some sort of casting. And if you do like SecAccessControl get constraints, and then you cast ACL to a SecAccessControl object, take the unretained value, and then again cast it as a dictionary, then you'll the constraint over there, the variable, you'll have a dictionary like this. So now I could use the Swift dictionary to manipulate this dictionary and access, like I could do the key value thing. Just step back to understand what this line is over here. Is that ACL by default comes in as a SecAccessControl reference, so it's still an object in itself. But the exclamation mark over there says that there is a value in ACL. So since it's SecAccessControl gets constraints as a C function, we cannot pass into it, and for that reason we need to tell Swift that there is a value in it. You can go call the C function, and take unwritten value is something to do with the ARC, the memory management stuff. So what this means is that so the object, the ACL object, is being accessed over here. But once this operation completes, then the pointer, so this is how the memory management works, right? So you have, if you have a number of pointers, then you have a count for it. So if you have like 5 pointers, you'll have a 5 count to it. And once you go through the free function, then those count get decreased to 0. Once it gets to 0, then that memory allocation is freed forever. So what take unwritten value does is that even though there is a pointer removed to it, it does not decrease the count of that object. This is important because when this function, it's written inside a function list line. So when that function exists, Swift automatically dereferences that particular ACL object. So if I need to tell, if I depend on Swift to take care of freeing that object, I need to do and take unwritten value. If I want to free an object myself, then I just do take written value, which automatically frees the object over here. And finally, I cast it as a Swift dictionary so that I will be able to poke it by just doing like a key value thing. So that's basically about SecAccessControl object. Now we know that we have a dictionary, and based on that dictionary, we can map out what constraints that the item was originally saved as. And Keychain editor, I'm technically not introducing it yet because this has already been released, and it's on my GitHub page. I'll also have a blog post on it. But the main features are that this tool provides you to dump the data, edit, delete a keychain item. It supports very well iOS 8 and above, and it integrates with IDB. So IDB is a tool, if you guys not already know of it, it's a static analysis tool written by my colleague for basically doing iOS pen testing. So the usage is that you have a detailed help guide to use. And I'll just show a quick demo later on. But some important functions are over here is that the action will either take like min dump, dump edit, delete. So minimum dump, so when I used to do pen testing, most of the times I do not know the account name or the service name of a particular item that I was looking for. So in order for that, I need to dump the whole keychain. But if I dump the whole keychain, it's basically like this with a lot of stuff, and I need to go through each one of them. But instead of that, what I did is that I just display the account and service name, so that's like a mini dump. And this will be a short list, and you could quickly go through what application you want to look at it, and you'll get the full reverse naming of it. So something like apple.facetime. So if you're looking at some application, you'll have com.companyname.application name. So that's min dump. And the other feature that I was talking about is the search functionality within the dump. So search is basically a contains operator on account name, service name, access group, and accessibility constants. So that means that you can specify action as dump, and then you say let's say you only want to find a list of when unlocked items. And you just do find when unlocked items, and you'll only get items that use when unlocked as an accessibility constant. So here only just three items. So likewise, you could just search for account name or service name, and you'll just get a short list of that. No need for everything. And I got a pull request saying that I need to support timestamp as well. I'm planning to do that soon. Also, this Keychain editor is like 6-7 months old, or I wrote this when iOS 8 was there, so iOS 9 was still releasing at that point of time. So at that time, only user presence was the only policy or constraint that was available. So I just used a pure Boolean value whether that item has access control or not by just saying no or yes. And edit is, again, like I said earlier, if you want to edit a particular Keychain item, then you use the edit action. However, there is a small thing to note that since it's a database, an item needs to be identified uniquely. And the way that an item is being identified is using a 3-tuple of account name, service name, and access group. So these, using these 3 pieces of information, you guarantee that an item is unique. However, access group is not required all the times. It is only required when, let's say you're dealing with MDM stuff, and since MDMs are complicated, so what that means is that when you're dealing with MDM, you will have a duplicated data of service and account name and service name. So one instance that I had to face was, so the RSA, iOS by default gives you an RSA library, but there was this MDM solution where it would also install its own RSA library. It's the same piece of RSA library, but MDM uses that RSA library compiled statically, so it gets installed, and that RSA library stores the same keychain item again onto the keychain. But since the MDM's access group is different from that of the iOS operating system, you need to have like a 3-tuple to get a differentiated version of like which item you're actually poking at. If you know for sure that you're not dealing with MDM stuff, then you're just guaranteed with the account name and service name that your item will be unique. And right now, I only accept base 64 encoded data because I don't want to lose any form of information when entering, because there are a lot of ways the data could be entered that might break the tool or just break the encoding format when it's inserted into the tool. And then finally, the delete, the same uniqueness to identify item uniquely, the same thing applies over here. It's just that the argument you're passing is one less over here. You don't pass any data argument, you just pass account name and service name to delete the item. And this is the IDV tool that I'm showing you guys. So this gives like a neat GUI interface. And the keychain is integrated with the IDB as well. So IDB could be run on your computer, and if you just hit dump keychain, it will call my tool. It dumps the keychain, and then you have like delete or edit buttons as well at the bottom. And today I would like to also introduce Keychain Editor UI. It's just the same tool, but I just wanted to learn Swift, and I wanted to write a GUI app for it. I just wrote a small UI application. I also used one of my close friends to help write that UI stuff that I really don't care about. But he was trying to mock me. He had a pink tab at the top, but whatever. It's again a similar set of things that it does. You could search for account name, service name, and then dump. Or if you don't give any of it, then a full list of things would get just dumped. So something like, the UI is not pretty. I'm getting there, working on it still. So this is, since this is still in, I think these screenshots are from the iOS simulator. So all the items are, so there are only 3 items for this purpose. And when you click on one of the account name, service name item, then you'll get a full list of items. And so you'll see that protection. The only problem right now, and then there is a delete button at the top, and then you'll have an edit button at the bottom. But anyways, the only problem for me right now is that I couldn't integrate the access control into the release version, is because there is a slight problem with how Swift. So I like Swift. Swift works really fast. It's easy to write, but it's not complete yet. And it brings a lot of problems when you deal with the bridging headers. So if you have, since I'm dealing with like undocumented C functions, it's giving me a few errors here and there, and it's not really stable right now. So I want to understand how Swift works, how the Swift's memory management works. Like I was telling earlier, the take unretained value was one thing that helped me stop that double free. I need to identify similar cases elsewhere in the code, and then I'll just have the access control as a new row over here, which will tell like which constraint that item has on it. So yeah, those are the two tools. Obviously, the future work is that obviously a lot of work remains on both these tools, and I'll try to keep updated with new versions of iOS, and hopefully it will be helpful for everyone and less bugs, of course. Internet passwords and certificates are not supported yet. I haven't had a case where I had to dump these items yet, but if there are enough pull requests, then I would think of dumping internet passwords and certificates as well. Again, iOS 8 onwards, there is iCloud Keychain, so the web sharing where the Keychain items get synchronized across all your devices. That is something that I have to work on my tool. And in general, I would want to go deep in the iOS Keychain stack itself. So, like earlier, I showed you the architecture of how the keychain works, and something to work is towards secure enclave, how the whole code path goes into secure enclave, how the keychain items are stored. So one thing, so if you were in David Schutz's talk, so David was telling that it's not totally clear like whether an actual item gets encrypted or the metadata for that item gets encrypted. From my experience, I think it's the metadata that gets encrypted, because this is only for keychain itself. So remember that I said that when passcode set, during when passcode set, if you use that particular accessibility constant and if you remove the device passcode later after the application installed, then that item gets invalidated by default. It gets deleted. That's what document says. But in practice, if you still, so if you dump that item, the item would not show. Fine. But if you use the command line tool and if you try to delete that item, then the item gets deleted. That is the point when that item gets deleted. So when I dug a little bit, I understood that since a lot of properties are added to for HFS plus file system, that is what Apple uses, there is a new attribute, not some new attribute, it's been there for a while. The attribute basically specifies that whether an item is accessible to the user or not. So when the key gets thrown away, then that particular item is like, set to unavailable. So you're never presented with that item, but it's still there in that memory. It's still there in the memory, and when I force it to delete it, then that particular item gets deleted. That is when it gets deleted. So interesting stuff like this. So I want to dig deeper into it. If you're interested, ping me. And if you ever use the tool, and if you encounter issues, please file issues on GitHub. And happy pen testing. I'll take any questions.
Have you done any work on iCloud Keychain?
Well, are you saying for the tool or in general?
Just in general. So, like, does it just sync the file? Does the SQLite database?
It does. It does sync the file across all your devices. The only exception is that if you see the only exception is when that if the accessibility constant is set to this device only, then it would not sync across devices, or it would not get backed up. So each accessibility constant will have its own set of keys, cryptographic keys for it. And this device only, the key is only stored within that device. So for some reason, if the key is lost, then that item is lost forever.
Got it.
So yeah. Anything else? All right, thank you guys. Thanks for attending.